So this is actually a Julia and Jump focused conference, but we have a tradition of inviting speakers from alternative modeling languages to come and tell us about their work. And this year, we've invited Ross from Google to come and talk to us about some new work they've been doing in Google OR tools. So Ross, take it away.
Okay. Hi. Thanks. So I'm Ross. Thanks for the invitation. So I work for Google and Google Research, and I'm on the operations research team, and we have an open source modeling, an open source library that includes mathematical modeling as part of what it does. It also has solvers. It's called OR Tools. And today I'm going to talk about MathOpt, which is kind of the V2 version of mathematical modeling for OR Tools. Okay, so what is MathOpt? So it's a library for solver-independent optimization modeling, and I guess for this community, I guess I don't need to sell the idea that you might want to do solver-independent modeling. That's what Jump does. And so you can access it from Python, Java, and C++, and there will be more languages to come. And it supports, we try and support like a wide range of features that solvers have: incrementalism, callbacks, duality, and some simple conic and nonlinear constraints. And we don't have 43 solvers, but we have a reasonable number of solvers, for at least for people who are interested in solving MIP problems. You can use Gurobi, and you can use skip and highs. So these are like, if you're license constrained or not, there'll be something here that does something good for you. And it can solve. This is kind of one of the interesting features of MathOpt. It's designed from the beginning to either solve locally, to solve in a subprocess, or to solve remotely on another machine. And when we say solve, like our goal is to support all of the features, including incremental solves and callbacks, when the solver is in a separate process from the modeling code. And so we use it in production at Google, and it's distributed as part of Google's open source OR tools. Okay, so a very simple example of just what the code looks like if you're a user. So let's say we have this very simple pip: maximize x plus 3y subject to x plus y is m-1.5 with an integer and a continuous variable. So first you would build the model, and because this is Python, we can kind of make the code look like the math. That's the goal. So we make a model, we add two variables, and then we can use the operator overloads in Python to build linear expressions to set up the objective and constraints. Then we set the parameters, and MathOpt, so we take it a little further than Jump in terms of these trying to have solver-independent parameters. It's a hard problem because the solvers are all different. But I mean, Jump definitely has enable controlling the logging is one of them. And then we call solve. And this is like just a one-shot solve. There's separate APIs for the one-shot and incremental solves. And so you set your solver to Gurobi, you get the result out. And here we're just checking that it was optimal and printing the results. So very kind of simple code for a simple use. So who are the contributors? So this is a bunch of people have worked on this. I'm going to try and say everything that's correct. I may make some mistakes because it's just a lot of code. So you can see here the top. There are three core Jump members in bold here: Miles, Joey, and JP. So a lot of the work that we've done is we took a lot of inspiration from Jump in designing this. And you may be wondering, JP, he's a manager. How does he have time to write so much code? And how you do it is you make a new project inside of MathOpt. You write 20,000 lines of code. Then you fork a file into 5 files, and you 5x your contribution. And then you move all that code out to a new directory and count it again. So that's how you get to the top. That's why JP's in charge. So anyway, so an outline for today's talk. Why MathOpt? And what is special about doing mathematical optimization at Google? How is it different from what you see outside? And then a little bit about how MathOpt is built. And I'll show some benchmarks and future work. Okay, so what are some applications at Google of optimization? It's not loading well. There's supposed to be some videos here, but oh, there we go. See if the internet is gonna. Well, okay, we may not get to see it all, but these are YouTube videos that just may not be on the internet or the internet connection's not working. Okay, so there are many applications at Google of optimization. Like you can see the bottom right corner, there are over, if you just look through the code, you'll find over 100 people who are solving MIPS at Google. Google has one mono repo, so you can look through the code. And the most common application is probably this kind of process machine assignment where you have tasks, you have machines, you need to figure out which machines are going to run which tasks. Very, very common problem at Google. Another big problem is in the supply chain setting where they're buying parts for the data centers and then shipping these parts around. But I mean, Google works on a lot of different things. There are network design problems, chip design problems. This robotics problem down here, this was actually done with a CP solver by the Google X spinoff Intrinsic. And these robots were being controlled by, like a CP solver was doing the plan of what order to move all the different arms in. Yeah, so many different applications. The one I wanted to show you that was a YouTube video, this is work from 2011 where they had a video that was shaky and then they solved an LP to make the video look not shaky. And that's interesting because it can run on the device or it can run on the server. So just another thing Google needs to be able to do. Sorry, the video is not working. Okay, so why is Google different? Okay, so we have great food, but I guess this was the wrong question. Why is optimization at Google different? So I'll give maybe 3 reasons, and like this is kind of motivation for why we built MathOpt. So the first thing is from a reliability. Like for many of our applications, it's very important that the code will never crash. In particular, we don't ever want a segfault for like if you've worked in C++. And we need to, like the users want us to give them a strong contract, and the users, if we break the contract, then the user's code crashes. So this like, we have to both have a contract and not break it. So this kind of goes into this reliability never crash. And why is this a problem for us? Well, the biggest issue is that a lot of our problems, I mean, we do solve strategic problems, and we also solve operational problems where you'll have a system that's solving, 100 MIPS every minute. And it's fully automated, so no one can babysit this. No one can babysit these solves. So it just has to be very reliable. And yeah, and as I said, if you have a weak contract or you break your contract, either way, it's going to result in a crash in the user code, or it'll slow down developer time, make it hard to write code. And we'll talk about how do we address reliability kind of coming up. So second, solve hard problems. And this is actually less specific to Google. Everyone has hard problems. Everyone has large optimization problems. Maybe something that is a little Google specific is this, like we do have some near real-time stuff where we have 10-second, 30-second time limits on problems that are pretty big because we're using it operationally, not strategically. And Google has this joke, I can't count so low. Like when you tell someone that like you can only solve things on like 100,000 variables, they're very surprised. They're like, that's a tiny number. What are you guys doing? I don't understand your field. So, okay. So last, from a maintainability perspective, and what do I mean by maintainable? What I mean is that we can safely make changes and be confident that we're not going to break something. And why? Because we can't crash. And why are there so many changes? So, like our code has dependencies inside of Google, and our dependencies are changing all the time. So we have to change as well. Users request new features, the solvers need upgrades, and like there's no branch. Everyone's building from head. So you have to be green. Everything has to work at every CL. So it's in this setting like you need to know that everything is safe when you make a change. Okay, so maybe these are the 3 things that we want to accomplish with MathOpt. And hopefully, now I'll tell you what MathOpt is, and maybe at the end I'll convince you that we did it. Okay, so maybe first I'll just give kind of a very high level, like what is the path from the user trying to solve a model to it actually getting to Gurobi. So hopefully this graphic isn't confusing. I've never tested it before. You guys are the first users of it. So what does the experience look like? So the user is writing Python code, they specify their model, so they make a model, they add a variable, they maximize that variable, simplest model. And like they're kind of interacting with the client library, which is returning stuff. Those arrows are kind of omitted from this picture. Then they make a solver object where they pass in the model. And what happens here? So under the hood, now we need to cross the language boundary to make the solver object. And the model is converted into this highlighted model proto, and this is using protocol buffers, which is it's kind of like JSON, but it's a structured format for encoding data. And it's a binary format. So we send the model down to the MathOpt core. Now we're in C++, and the MathOpt core will then go to Gurobi and say, Gurobi, please make this model, add the variables, update the model. Then the user calls solve. So they set their enable output to true, and they call solve, passing the parameters down. Again, we need to cross the language barrier. We send the parameters down as a protocol buffer. And inside the core, we then tell Gurobi to set the enable output true and to call optimize, and we get the result back. We extract the result from Gurobi, and we build a new protocol buffer, which we then send back to the client library, which then sends the result back to the user. So this is kind of the flow. And in different languages, you'll have a different implementation of the client library, but it's going to do the same thing. It's going to send protocol buffers back and forth. Yeah.
Why are we using protocol buffers here? Is it because it's running on a different Docker container or a different...
Yeah, so this is a good question. So we want the flexibility to run the core in a different process or in a sub-process or on a different machine entirely for remote solve. But even for local solve, there are some advantages to having this strong separation between the client and the server. And then the question is, like, can we afford it? How much does it cost us to go through this extra layer? And we'll return to that at the end of the talk. OK, so the kind of big pieces are the client, the binary protocol, and the core. And so why did we split up the code this way? And I think Jump has converged on, I'm not an expert on the Jump code base, but I know that you have Jump and you have MOI. So I think you have something similar going on. So separation of concerns, this is like the biggest thing. The client is actually more code than the core. And we don't want to think about the complexity of the client when we're working in the core and vice versa. And like by isolating everything, but going through a pure data format, it just makes it a lot simpler to reason about the code. And also from a modularity perspective, if you don't like your client, you can write a new client in C++ or Python and just reuse the core. So inter-process communication, as I mentioned, like this kind of gives us inter-process communication for free. Another big advantage, and this is something that you guys have in your caching optimizer in Jump, is that we can do, when you interact with the solvers for efficiency, they want to work in batch operations, but the user never wants batch operations. They just want to set and get one at a time, because it's a lot simpler. And we're set up to do that in this setting. And last, when something goes wrong, we can just replay the sequence of protocol buffers to reproduce the crash. OK, so I guess I tricked you guys. The talk just got twice as long. So I'll talk a little bit about each of these three pieces, and then we can kind of return to the main bullets. So what do these protocol buffers look like? So here's like kind of a stylized subset of the model proto that we have. And so there's a message for the variables, a message for the objective, and then the message for the model contains the variables and the objective. And within the variables, there are IDs, lower bounds, upper bounds, and integrality. And so why are there IDs? So we support incrementalism, and when you delete something, when you delete a variable, we don't shift everything down. The IDs are stable. There are pros and cons to doing this. It's just the choice we made. It's a little bit simpler for the user this way. So it's a structured data format for encoding your model. And it's widely used inside and outside of Google in the software engineering world. And there are lots of alternatives to protocol buffers, but this is kind of just the one that is most widely used in Google and has support in many different languages. And so what's nice about this is that you have this, you write down this proto file, and then it generates code in Java, in C++, in Python to help you build these messages. And then we can cross the language boundary as bytes. And so you can see here that like we did, the variables proto is organized as a struct of arrays instead of an array of structs. Like array of structs is easier to work with. Struct of arrays is a little bit faster for languages like Python or Java where there's a lot of overhead to calling new. So that's why we did it. I mean, it was a small win. I don't know if it was worth it, but we did do it. So, okay, and then how does incrementality work in the protocol? So you have this idea of an update proto where you say, what about your model has changed? So some variables were deleted. Some variables have their bounds updated, either a lower bound updated, an upper bound updated, or integrality changed. And then you'll have new variables that you've added to the model. And then there'll be more in this model update proto for constraints and objectives. And so our goal was just to build the smallest possible message to encapsulate the update, because we don't want to send the whole model and then diff on the server, because like we don't want to use, I mean, it's more CPU time on the server and more network space. So it's the client's job to build these diffs. And it's a lot of code to build the diffs, but it's more efficient. Okay, so when you have a delete, you just send the IDs of what's been deleted. And everything, any constraint using a variable that was deleted, you don't just send that constraint has been updated, just that's implicitly zeroed out. Yeah. Okay, so, and kind of the last part about this, these protocol buffers is that we have a strong and programmatically enforced contract. And this is, what do I mean by this? So in every protocol buffer, there's going to be a comment saying, what are the rules for this protocol buffer? So the IDs need to be sorted and unique and non-negative, and in this sparse double vector proto. And the values cannot contain a nan, and they must be an equal number of values to IDs. So you have these kinds of contracts in the messages. And then in our solve function, when we call solve, we check. We have a function that will check that the contract is met and return a status error if the contract is violated. And then we can propagate this error in the, so like in C++, in C++ we don't throw exceptions to Google. We have to return an error instead. And then in Java and Python, this will be propagated as an exception. And we check the input to the input model, and we check the output solve result to make sure that everything is OK. And so this is good because it means that we can actually have a contract. If you guys have worked with the solvers, like you'll see they have a giant API, and there's no guarantees as to when any field is going to be populated. You just have to check to see if it's there. So this is something that we're trying to be more precise on. So why do we do this? If you provide a strong contract, user code is a lot simpler. Don't need to have a bunch of conditionals. It makes you end up testing a lot more when you have your unit tests, and you have a powerful combination with a fuzzer. And so this idea of a fuzzer is that you generate random protocol buffers, send them down to the solver, and see what crashes the solver. And this validator catches a lot of issues. Okay, so got to speed up, using a lot of time. Okay, so next I'm going to talk about the client library. So what are the responsibilities of the client library? You need to be able to add, delete, get, or set in O of one time for any property of the model. And you need to be able to access the rows and columns efficiently. That's our goal. We need to be able to build these protocol buffers for the model and the model update. And we need to be able to generate our constraints with operator overloads. So if we want to get or set our coefficients efficiently, what is the key task? We need to work with a sparse matrix. We need some way of dealing with this. And it's because our IDs are sparse after deleting variables. Like we are kind of three-way sparse. We're sparse in the rows, we're sparse in the columns, and we're sparse in the non-zeros of the matrix. And then you kind of have all these basic operations of set and get. And the ones that are kind of tricky are get all the rows, get all the columns, and delete a row or delete a column. So the simplest solution you have that gets an asymptotically optimal performance is that you just hash everything. So you have a map from the rows to from the row ID into the column double values, and then you map the other direction from the column ID into the set of rows that have non-zero value. And then so this is a lot of hashing, right? But like you can get an optimal result here. And then when you delete, you just have to, when you want to delete a column, it's a little tricky, but it's relatively simple code. I'm actually going to skip this for time. And we can do better in terms of like reducing the total amount of hashing our code uses with more complicated data structures. And in C++ we do it, in other languages we don't. Okay, so I'm just going to skip this how do we build model update protos because the slide is kind of long and we're out of time. On variables and expressions, so the last responsibility of the client library is to like, so users don't want to interact with ints, they want a type-safe API. So when you say model to add a variable, you get back a variable object, not an integer, and you can set the lower bound directly on that object. And then we have to overload the arithmetic operators to add constraints. And then there's a question of, when you have linear expressions, how do you want to represent them? So in C++, our linear expressions are just a hash map from variable to double, and then the double offset. In Python, we do something a little more complicated, where when you call multiplication or plus, it actually is building an immutable abstract syntax tree, and then you have to flatten it before you can read it. And why do we do this? We'll see on the next slide. And last, we try and leverage the compiler to make it so that way, like you say add linear constraint and you add a quadratic constraint, it's an error. You're stopped at compile time. Okay, so maybe some gotchas. These were kind of fun things about linear expressions. So first, okay, so I have two variables and I say variable x equal variable y. So is z a Boolean that indicates if they're the same, or is z a linear constraint? So do you have to decide? You don't have to decide, you can have both. And the idea is that you have an object that's both implicitly convertible to a Boolean and to a constraint, and that you can do this in Python and in C++. I don't know how does Julia deal with the situation?
We don't.
You don't. Okay, that's a good answer. Like, was it wise to do this? I don't know, but we did it. Okay, another kind of gotcha here. So if you call the sum function on the Python's built-in sum function on a list of variables, what is the running time? Is it linear or quadratic? And the same issue occurs in accumulate. And the reason why it can be quadratic, depending on your implementation, is that the sum function uses the plus operator, like the x plus y operator, not the plus equal operator. And so you can end up doing, if the plus operator returns something that is equal to the full output, then you end up doing a linear amount of work for each plus. So that's why we do this deferred evaluation in Python. And just some random stuff that has burned us in the past. So this is on the predecessor to MathOpt in C++. The following code compiles, but it does not do what you want. So here I made a variable. The variable is a pointer. That's the type of variables this is how we represent variables in MathOpt. And I add 8 to the pointer and then convert it to a linear expression. And I am not getting x plus 8. I'm getting pointer arithmetic into garbage memory and bad time. So this is something that we avoided in MathOpt by just not using pointer types to represent values. Okay, so I think that we're just going to skip this next section. So this is like kind of on the solver side. It's probably the least interesting of the sections. So we'll skip it and go straight to the benchmark. Okay, so here's a very simple benchmark I did on the traveling salesman problem. So the goal here was to measure what is the overhead of MathOpt in a callback. So the setup, I took 100 cities on IID in the plane, and the distance metric is Euclidean. And we use this kind of standard cut set bit formulation. It's an exponentially large formulation where you need to separate over the constraints as you solve. And I use a callback to add the constraints at every fractional solution. But I don't do exact separation. I do heuristic separation where the time to separate is like linear in the size of the number of non-zeros. So this is, I mean, the details aren't super important, but it's very basic TSP stuff. And then I solve with Gurobi in one thread. And so we'll look at 3 settings. So just Gurobi. So here this is measuring. So this is actually, it's milliseconds, not seconds. The axis is wrong. Sorry about that. So if the time that was spent inside of Gurobi was about 500 milliseconds, and the time that was spent inside of MathOpt was like, I think it was 590 milliseconds. And then kind of this third bar here is what if MathOpt's in a subprocess? How much time did it take? And now it took over a second. So how much of this time was because of subprocess startup overhead? How much of it was because of communication with the subprocess? You can't answer that from this plot. I apologize, and further experiments are required. I guess you'll have to wait for a paper if you want to know the answer to that question. But I believe that the main driver here is actually subprocess startup is probably about half a second. So, okay, and last demo. So I'm not on the internet. Okay, well, I guess we'll have to skip that demo. I was going to show a demo of the C++ code running in a browser to solve a MIP. And this is done using WASM. So like the point is that the C++ code is portable. It can run on Android, it can run on iOS, it can run in the browser. Okay, so future directions, more languages. We need to catch up in Java, Python. We want to get Go and JavaScript. And we also want a C API, which so that way any language could wrap our solver. And if jump wants to call GLOP or PDLP or CPSAT, this could be one path. They could also directly connect to these libraries, but the nice thing about using MathOpt is that the API is very small. There's only 3 methods that we need to wrap in the C API. So we want to add more constraints. We want to add more solvers. So another thing is we need to catch up in open source. Right now, only the C++ stuff works in open source. So we need to fix our build system. All our documentation is internal, and we need to get our RPC mechanism that we use is an internal only one. So we have to switch to, we need to get a version working with gRPC if people want to use the RPC stuff outside. And JP, I don't know if you see JP's talk later, he may be talking about how do we do a better job on making it easy to write decompositions. Okay, so to kind of wrap up, MathOpt is Google's solver-independent modeling library. And so what were our 3 goals? Reliability. So how do we achieve this? Input-output validation, solve in a subprocess, and write your clients without any C++ on the client. This is the best way to not have a seg fault in your code. Powerful. So we had a bunch of, we try to support a wide range of features that make it possible to solve really big problems, and maintainable. So separation of concerns. This is all basic software engineering stuff. Encapsulation, testing, that's the goal. And it's built for Google, but free for you if you use OR tools. And as I said, the open source stuff is lagging, so hopefully it will catch up over the next few months. Okay, thanks.
So we have time for a question from Miles. And I might just ask that you restate the question
Yes.
into the mic for the video.
Okay, so the question was, so in protocol buffers, if you need to serialize a protocol buffer, you have a limit of 2 gigabytes. And even if you don't serialize it, if you have a vector in a protocol buffer, you're limited to 2 to the 31 non-zeros 2 to the 31 elements in the vector. So right now, I would say that for serialization, okay, the answer for both is no. We have something planned, but it's just not, we haven't worked on it. We will work on it when there's a user who says like, Google is losing money because this doesn't work. So it will happen soon.
So, question.
So you just now mentioned about some decompositions that you are doing that's sort of helping with making those large problems solved faster. Can you say something about that?
Okay, so I think that the canonical reference that we have for like a big problem that we worked with better job on in decomposition with MathOpt was, so Google has a partnership with Lufthansa where they have to solve this operational problem of they have to, you have, like there's a disruption in the schedule, you have planes, you have passengers, and you have crew. You have to decide who's going to go where to get back on schedule. And like this is a multi-tiered decomposition that they solved the problem with. There's a lot of column generation involved, and like MathOpt was used to make this a lot faster, especially on the airplane rotation side. So that's maybe one example.
Thanks, Ross.
Yep.